Thanks for coming. And thanks Intel for holding this event. And all of you who contribute code to the SPDK community, highly appreciate it, especially those of you who don't work for Intel, because diversity is good, right? All right, I'm Patrick. I'm a cloud solutions architect. And it's a three-part presentation. I want to cover a little bit about our company, who we are, what we do, advertisement. But then I'm going to talk about something more important. That's our TCP/IP user stack. It's called OnLoad. And then I'll talk about all the work that we did of porting that to SPDK and why we did it, and a little bit about what's going on there and the roadmap for it. OK? Oh, and make it interactive. I'm not here to bore you. You have a question, we'll get you a mic. And I'm going to be throwing out a lot of rhetorical, somewhat questions, and I'll answer them myself. But the point of my presentation here, I don't want to be up here preaching. I want to be up here to try to make you think differently or look at problems maybe a little bit differently. And I'm also here to learn. I'm not here just to say things, right? All right. So who are we? We're a solar panel company. No, we're not. That's Solareflare. That's just our name. We're actually a networking company. But we do get calls from solar panel people. It's true. All right. So then, and then interesting company because I don't know if you guys ever been to Cambridge, UK. It's a very different culture there. That's where physics was born. That's the home of Newton and Darwin and all those guys. First time I went there, like the taxi driver had a PhD. And then I'm like, everybody here has a PhD? He goes, well, the ones that don't are in a PhD program. So it's quite. And then our other half of our company is in Irvine, California, Orange County, California surf culture. I don't know how this company works, but it does. So it's a diverse company, right? So let's see. All right, so what do we do, or what are we known for? The world economy runs on us. Why do I say that? 90% of the capital markets in the world are operated on our technology. Why? Because we specialize in low latency networks. And this is the lowest latency. When I'm talking about that, I'm not talking about across the internet. These people care about nanoseconds. So they put this is inside the data center. They put their servers, colo, next to the NASDAQ server, and they care about how long that wire is, so that we have to shave every nanoseconds we can. That's our background. But there's certain trends going on in the market, as you would know. Hardware is becoming commoditized, trend number one. Trend number two, software is becoming open source. Trend number three, everything's moving to the cloud. So what are we doing now? The last couple of years, we've taken this proprietary, cutting-edge Wall Street technology, and we're trying to leverage it onto the cloud market, right? All right. So as far as what we do, the sort of the cards, yes, we can make adapters. Everybody else. We have them in all form factors. When a new form factor comes, like OCP, yeah, we get them. When a new PHY comes, we have to have different speeds, like 100 gig. Yes, we make it. But more importantly, we're spinning silicon just like Intel every 18 months or more frequently, because as the geometry shrinks, it may only get you a few nanoseconds, but our customers want us to do that. So we always have to have new chips, and we constantly have new products for that market, right? OK, so that's all I had on the first section, which was our products. Now, what is this graph? I don't know if you've seen it before. But I think this graph should be, or this slide should be in every presentation. To me, this speaks 1,000 words. In the 90s, things were good. I was young. I had a lot of money. But then, no, what was happening is that there was no issues with bottlenecks in the network. All we did was I had my first computer, I don't know, how many was it, like 20 megahertz? Then I would just get a 40 meg computer, and things were speeding up, and you would just clock up, clock up. We started right around there, our company, where the frequency, we couldn't push it up. We're going digital frequency. Digital logic, we can't go above, what? It's not 4, 5, 6. You can go above that, right? So then that's where, which is fine, but that's something interesting that happens. This would have been fine because it saved me power, but as you can see, the single thread process performance suffered. By the way, this is not a problem specific to, this is a problem specific to the world. This is not, this is specific to anybody. It's for everyone. What's good is that this thing's still growing here, the number of transistors. But we need to find more innovative ways, obviously, and that's what we're doing last decade and a half, where as the number of cores increase, we have to come up with more clever ways to get rid of system bottlenecks. And we focus on the network part of that, solving that problem. You guys are working with companies that may work on the other aspects of it. Obviously, things like SPDK, DPDK, the stuff that Intel's doing addresses these issues, right? So now, but this, I don't want to talk about Moore's law, this and that, if it's dead, if it's alive. What's important is this: if you extend Moore's laws, which Ray Kurzweil did at Google, there's good news. If you look at the cost of computing in the last 100 years, for how much computing you get for $1,000, that's going up exponentially, and that needs to stay right there like that, because if it doesn't, our standard of living will become stagnant. The kind of things that I can do today because of this graph is like I can have that more transistors in my cell phone than all transistors used in World War II. You can have a couple of guys in a dorm like Zuckerberg that can start a multi-billion-dollar company because they got access to computing. I can put down my credit card at AWS and solve supercomputing problems. If that curve needs to grow, so that's important for us, and we're part of that, right? So, and then that's, anybody know who that is on the corner there? Obviously, young Gordon Moore, right? So, what do we focus on? We can't solve everything. That's classic von Neumann architecture, right? But the ecosystem here, and many of you here work on different parts of it. You got the application. Application could be the bottleneck. A lot of times the software is. Software's not written well. Kernel could be the bottleneck. CPU could be the bottleneck. There I got to rely on Intel and AMD and ARM and all that. Memory, I got to rely on the memory people. That could be a bottleneck. A lot of times memory's easy. You add more memory, but then we talked earlier talks. You saw that we did other things to address those bottlenecks. And by the way, I didn't even know you had this product, Retune. That's beautiful because now I can use that to figure out where I'm looking at the entire system architecture of a real application. My focus this year is not to look at the vendor's perspective, but look at the customer's perspective. Use technology, use something like SPDK to solve real-world problems, work with real people, work on real-world problems, not just come up with something because it's fast or it's cool. No, we got to address real things, and there's always going to be a bottleneck in one of those devices, and that's where we need to solve. And when you solve that, guess what? Bottleneck moves somewhere else. So this is a never-ending problem, and I listed the places where the bottleneck could be. Right above, who's that over there? That's John von Neumann, right? There. So I can't change your code. Application, you guys got to do it. Or people, Redis and Nginx will do it. Kernel, I can help you there by bypassing it. So can SPDK, so can DPDK, and so on. We sit on top of those things, right? CPU, can't do much there, but Intel can. Memory, again, can't do anything about it. Storage I/O and network I/O, however, that's where we specialize. So bypassing the kernel and then doing I/O, those are the bottlenecks that our company can solve. So little quick math here. You should know this. I know this by heart. But I think a lot of times I've seen a lot of people make a mistake or because, I don't know, we're brainwashed maybe because of the cable companies and home internet access, that we care about bandwidth. Bandwidth's a trivial problem to solve. And it's rarely, I work with a lot of customers, it's rarely a bottleneck inside a data center. It's a major bottleneck in the internet, but not in a data center. Those links are underutilized because of other bottlenecks. But bandwidth is, and also, let's just say you do have a bandwidth problem in your data center. What's the easiest solution? You don't even need to upgrade your technology, go from 10 to 100. You can just add another port. Because the number of millions of packets that today's modern Intel processor can serve with some like DPDK is what, 5 million packets per second? That does the job. So I want you to not think about bandwidth. I want you to think about a fundamental problem that we work on, which is latency, that is very difficult not trivial to solve. And also, when in bandwidth, you just convert it to that. Convert it to packet rate and think of bandwidth as processing. And we can help you there as well, right? So, talking about, so there's been many approaches. I mean, DPDK is the latest, but before there was ever a DPDK, we had something that was called, but that wasn't called DPDK, but it was DPDK. It was very similar. It was called EFVI, Ether Fabric Virtual Interface. But that's kind of a niche. It's not open source. It's proprietary. It's for the financial markets. It's for the traders. But we had this 10 years. We had this in 2001, right? And then obviously the other MPI type alternatives are there as well, and they still exist. It's good. Free market. You have a lot of choices, right? So, I mean, basic solution is this. It's many people do it. They just do it different ways. How we do it differently is that it's that little thing right there. Sockets. We're POSIX compliant socket base. I mean, so today basically what I'm announcing is that, and I don't know if you guys have, VPP is not POSIX compliant. Some of the customers may need that. The stack that we ported is. It talks to sockets if that's what you want. How many people here use VPP? Is it probably that's basically the official TCP/IP stack that's more mature. Last year Cisco was here presenting it, right? So what happens when you do this? We solve a lot of those I/O issues that I was talking about, network I/O. So you get the lowest latency, you get the improved packet rates, you get efficient CPU utilization, measure that in power. So yeah, this technology is called onload. We had an earlier presentation, people talking about offload, different philosophies. I'm betting on Moore's law. I'm betting on Intel being competitive and the CPU prices keep dropping and the CPU power keep going up and the number of cores increasing. But then how do I get my benefit? I don't offload, I use the CPU more efficiently. The kernel does not use the CPU efficiently. So those are optimizations we do. It's a completely opposite, it's not even intuitive because you think, what's the fastest thing to do? Offload things. Well, that's a different strategy. We're about efficiency. Also, you got to be careful about this. I see many people offload, and they go, oh, look, CPU utilization is down. Application can use it. Go monitor a real system. The way applications work, you got to have a certain traffic pattern, and that scheduler has got to be pretty clever to not actually go in and use that. And by the time he does all the context copies and tries to get the stack and the heap and move it and do the memory copies, it's very, usually if you want to run a process fast, you stick to one CPU. Those offload CPU cycles, depending on your environment. If you're doing something like clever things, you could use them. In a cloud, you could use it. But I'm just saying, you got to have the right environment for it. And then also, obviously, the other benefit is the kernel has a lot of jitter. Predictability is important. Measure that in standard deviation sigma. And then, because this is the other thing. Because this is TCP/IP, I don't need to go get libIB verbs, or I don't need to go some other library. Most applications are written on TCP/IP. It's very easy to port your application, and we try to make it even easier. And that saves in your R&D, right? Okay, so here's how it works. Now, there's an hour-and-a-half Google video on this. But before you watch it, get a lot of coffee. You may fall asleep. It goes in depth in it, and I'll put the link up somewhere that goes over this in detail. But I just want to give you a general idea of how it works. So it's transparent to the application in the case that Andy was talking about the only way to get to the kernel, socket calls. That's the only way you got. It steals those socket calls, but the application doesn't know it. But it doesn't steal all of them. Only the ones that we can accelerate, it steals. How does it do it at runtime? You guys familiar with LD preload? It's a link shared library, dynamically linked shared library at the runtime. You load it up. Now you unloaded your application. There's more to it. I'm oversimplifying it, but that's the idea. Right, so that, if you don't use that, and it works in parallel with libc. Why is this important? Let's just say you don't want to, or something that can't be accelerated and stuff. Well, that stuff will still go through the kernel. Let's say something breaks, there's a bug in it. That stuff, the stuff that we cannot accelerate, we send through the kernel. So it's actually both a kernel and a kernel bypass parallel strategy. And so, we intercept those calls, and that's the name of the library there. But that was all sending out data. For receiving data, we have filters that we intel, and that goes through the thing. But how am I doing on time? Yeah. So you can go through you could go through that video if you're interested, or talk to me, and we'll get you more details. Questions so far? All right. So what have we done so far with this outside of high frequency trading and flash crashes and all that? Not every application is going to be network bottlenecked. So one of our jobs is to look for things that are. And these are the 7 categories that we found so far. There are other ones that we found. So web servers tend to be like that. Proxies, load balancers tend to be like that. In-memory databases tend to be like that. Message brokers tend to be like that. Sometimes with DNS routers, you could get some advantages. But we got 2 new technologies kind of emerging. If you're familiar with a company like GridGain or Apache Ignite product, they do in-memory compute grids and data stores. So let's say the bottleneck is the disk or the memory or something. Well, those things those will bring up data in memory and solve those and already get rid of that bottleneck. But I told you, every time you solve one bottleneck, there's always another one. So they're perfect for us, because then now we can take almost any app, like not any app, but the big data app, and if they're using some sort of in-memory data grid, now it's going to be network bound. Now we can help you. Okay, so that was the second segment of bitches. That was our TCP/IP user space network stack. It's proven. Financial industry. We've had it for how long, Simon? How long has this been around? 10, 20 years? It's bulletproof. So, because there are not that many, I don't think there are that many mature ones out there that are actually run in production. So what do we do with it? Now I want to talk about the storage part. I want to move to storage. So you guys all know these, all the different buses we went through and the evolution of a bus. But these things are converging. Yes, of course, every bus has its own thing. And for the longest time, SCSI was the standard for storage. But as we now know, everything's going to go towards PCIe, right? So SAS and SATA on the decline. Okay, we got to note that fact. Fact number 2, this thing. Who's still using HDDs? If you are, you're wasting your life, because it just takes so long to get to that data. And solid state, the prices are fair now, and you can get your data a lot faster. You don't want to be waiting for that. Now, other than the fact that we all know has a lot of queues and all these other good things, and it doesn't have a mechanical. It doesn't have a mechanical part, so it's not going to have mechanical failures. But then it does have a lifetime. We know all that. But we got to also think about, how does this affect the network from our perspective? Oh, sorry. We know. Okay. If we're going on a PCI bus, it doesn't make sense to not have that SCSI layer. That's why we have now. That's how NVMe came about. And there you go. You see it. It's many orders of magnitude. The latency is less, and you're bypassing the SCSI layer. But also from a network perspective, before these SSDs were around, we needed very special networks. So what is the impact to network now that we have this? Because remember, let's just say you're in a classic storage network with a spinning spindle disk. Packets get dropped. Now that and packets will get, then that needle has to go back. It would be just too costly. Right now, the networks inside data centers are very efficient, and if you design them correctly, you don't really have to worry about packet drops as much. If you have packet drops inside your data center, you have bigger issues than your storage network performance. So this stuff with lossless network, yes, you're welcome to set it up and all this stuff, but it's becoming less necessarily, in my opinion. You're welcome to disagree. That's what I'm seeing out there. The other trend that I'm seeing is this. And if you don't believe me, go ask EMC and NetApp, who made fortunes on the architecture above, which is, this is how we used to do it. You used to get some sort of dedicated network, fiber channel, used to have big proprietary boxes. You had a bunch of servers in the front, but it was expensive. It was somewhat monolithic on the back end, and you could have bottlenecks. Well, Google and Amazon started this years ago, but now it seems like other customers are going this direction, and that's what they're going back to DAS. That used to be a bad word 20 years ago. Now it's like going that direction again. So low-cost DAS-based scale-out clustered file system seem to be popular again. They're coming back. It's like fashion. But so then, what's the point of do we even need? Now the question becomes, are we going to even need storage networking? If that's the case, well, you got to do the math. This is a bit complex. I don't know if I have time to go over it. But this is from Stanford University. Again, I'll put the link up on my LinkedIn, or on my GitHub or somewhere. Stanford and Facebook sat down and did this, and did the cost models and did the math. I'm just going to give you the big picture. Remember, so now you're going to have the server architecture, which I mentioned. It's all going to be DAS. But then you got to have a tier of servers that's compute, a tier of servers that data stores. You're not going to have a big monolithic box that's like storage based. But does it not make sense to separate out the storage? Because it ends up being, it could be more costly if you're going to serve that disk over the network. I mean, why do you have to, if you design correctly from the first day, if you want to design, I'll go back to this slide. If I want to correct the data center from the first day and I know how my data load is, see those servers down there? Well, I would calculate what the ratio of my CPU to RAM to storage is and get it like that so I don't have to worry about it. And these are all built on scale-out software, things like, Ceph and OpenIO and Rook and all this, all the cloud native type applications, where it's all fine. But something tricky ends up happening, and that's that needs of applications over time could change. Think about Facebook. When you first started Facebook, those servers, they thought, okay, you would only need this much space. But now that application needs more space. Applications change. Applications migrate. So then, yes, there is still need for network storage. The cost formula for it is this. There is a tax you got to pay, and that's that delta there after the F. And this is according, by the way, this is from Stanford University and Facebook, right? So so if it makes sense to you, and it does make sense to hyperscalers, then we're in business again because now they have a need for network storage. So, but what kind of network storage now? Now here, remember, it's just a server serving. By the way, you could have a NIC, you could have a smart NIC that does all the things, so it could be like a JBOD, so there's no processors, but then that NIC could be expensive, right? So this sort of takes into account all that. So if this makes sense for the customer, then good. Now now that buses have changed and we've gone to solid state and all the other changes that I mentioned to you. Now here are your choices. IB, Rocky, iWarp, TCP/FC. So obviously we did all the TCP work, and we focused on the TCP part. Why? Because that's the most prevalent network out there, and that's the one that's just very popular and easy to set up, and you don't really need to do anything special with your switches, and you don't need your cards to support like RDMA and things like that. But there's a cost to it, and I'll go over that. So what we did was we started in a company called Lightbytes, Sagi Bromberg, you may know him, he wrote a lot of the code for Lightbits. But we wrote an initiator and a target kernel NVMe for TCP, not for RDMA. That was the first thing we did. And that thing's now submitted to the kernel. It's 4.18, Sagi backported, he has it on 4.18, but you're not gonna get it for free in the kernel until 5.0. Major distributions are not on 5. The only one I know that is Fedora 29. Maybe Debian, but I don't have Debian, so I couldn't tell you. But so what do you do today if you want this? We actually backported it to all the Red Hat 7X stuff, right? So if someone wants to do that today, we have that code. Or they can wait until Red Hat and Ubuntu and the popular distributions get to, Red Hat's still on 3X kernel until they get to 5.0 or they backport it. I don't know what their plans are. So that's the stuff that I was talking about, so that's what we did, right? So what's the problem with this? Well, performance. You saw the Mellanox guys. RDMA gives you awesome performance. Is this performance even acceptable? Is this good enough? Through the kernel, maybe for some applications. So those are the kind of benchmarks that we got to do. And we have done, and I can share those numbers with it. But there's hope, because we can do something more clever with SPDK, right? So what we did was, if you use SPDK, we talked about SPDK, and we also talked about NVMe is going to bypass all of that. It's perfect complement to SPDK. It's like going to put all that stuff, it's going to bypass the kernel. So, but then your network problem is still not solved. DPDK, fine, but doesn't, you don't have a TCP/IP stack on there. Well, you have BPP, but it's not sockets compliant. Like I said, that's what's different. We ported all the onload that I was talking to you about onto this. So now you finally have that's the option of this camera. You finally have a POSIX compliant user space TCP/IP stack that we wrote. And that's what I want you to, if there's interest, that's what I want you to test. That's what I want you to play with. So let's look at some numbers. We didn't get a chance to. I don't think there's any room out there to do the demo, but I have something like this set up in my lab. It's just like every other demo people show, just 2 servers, but switch in between them. And we put the initiator and target there, right? Also supported that I have a version running on the cloud as well. What's beautiful now, it's like we got to, for people to actually contribute, especially for this community to get bigger, for more people to be able, we need to give them access to hardware. That's why I like that Intel Builders program. But on top of that, Amazon now has, AWS now has Metal instances, and you can put I've ran DPDK on there before. So when you get that, you make SPDK that easily accessible. More of the people, especially the younger people, are gonna get into it, and the community is gonna grow. So, okay, back to this. This is the performance, right? And I'm not trying to get into bits and bytes of it and the numbers and stuff. And this is some preliminary numbers. I'm not showing this to go, this is better, that's worse. But it ends up being okay. SPDK on load. The performance is more or less roughly, of course, it's going to change. This is block size of, this is 4K block size, random reads, number of jobs is that. You change those parameters, things are going to change, right? There's no fixed standard benchmark for any of this. But that's what you get. You roughly get, it's on par with the RDMA performance. That's the point. This summarizes those numbers. So yeah, there are cases where we're worse, there are cases where we're better. For ultimate performance, obviously, if you take RDMA and you get SPDK, you'll get better than all this. And I haven't seen the numbers, but they had it. I just saw it. I didn't even know they had offloaded SPDK. But if you offload SPDK, I would guess you would get the best numbers, but I'm not sure. Because I got to get a hold of that card. Questions, thoughts? Yes?
How do you bypass kernel for the block access from the initiator side? It's still...
Oh, yeah, this is, sorry, good point, thank you. No, this is target only. On the initiator or onload, you can do application, but not on the block storage. Yeah, no. You have to write some sort of file system and stuff. We thinking about some things out there, but yeah, that's a good point. Thank you. Yeah.
Thank you. Hey, so my question is on the latency number. I think you have a typo, but that's not a problem. So it's 22 microsecond versus 19 microsecond, right? So what did that number really include? Is includes the SSD access time as well, or just a purely software?
Right. So that's FIO. What did it say? Nanosecond. I got to check why that. This should be. That's not right. So that should be micro. But no. This is going to be. We run FIO on one end, right? And then we go over the network, and then the block storage is presented over the network through the protocol mentioned in the last graph. So that's how we're measuring it. FIO block size. Yeah.
Yeah, but in your previous setup picture, you showed that is Samsung SSD, right? That's Samsung 1750. So what's the latency in the SSD itself?
Like the spec. I don't even know if that setup relates to those numbers, or I think that guy was running a Dell number, but I think it's the same parts. Those numbers may be off. I don't doubt it. But like I said, we can get you I have a bunch of benchmarks that I can send you. Okay. This is a demo I have. So let me just separate you. This is a demo that I have set up in my lab that I do my test on. The numbers that I got on that graph, that was like some preliminary numbers on some testing that engineering did. They did not use this servers, maybe not even that those drives, right? Okay. So those are different.
All right, thank you.
Yeah.
Another question over here.
Yeah.
Are you guys going to support Windows at all with NVMe or NVMe TCP at Solareflare?
No, because no. The answer is no. We're all Linux, and FreeBSD has its own, so you're even a step ahead there. But all flavors are Linux. Yeah, it's not a Windows technology. Okay. So we know.
Hold on, we got one more question back here.
Questions? I love yes.
And RDMA API has been designed to make it easy to implement zero-copy I/O. With BSD Socket API, it's very hard to implement zero-copy I/O. How does your API support zero-copy communication?
Yes. So those are the details that I'm going to give you an honest answer to, because last time I wrote code was 1985 and it was Apple IIe computer. So my engineers can kind of tell you the details of how that's done. Okay. Or any serious code. I just goof around now. All right, so these are numbers from Intel site, right? And these are probably older numbers, and I got to update that. We got to get the better numbers. But my point is, you guys get it. You got to mix this. You got to solve the network side, and I got to play with BPP too. I'm sure those numbers are good. But we got a bigger challenge ahead of us, and that's this. So when a customer goes and wants to, again, I'm looking at this from a customer perspective. I'm a DevOps guy. My boss tells me build a cloud. What I do is, this is why I love the work that's getting done with OpenStack, and we should support that more. Because I'm gonna go get OpenStack, and I'm gonna use whatever it uses by default. And you know, what is it? Is it Swift? Not what's the block storage? And what I forgot. Cinder. Cinder by default is like iSCSI, I think, still. But so we need to basically for this to be successful, because this SPDK is solving a lot of bottleneck problems. But then, unless we work with we do a better job of integration, and we figure out which software stacks are popular, like Ceph and all that, and then we make it somehow be the default or an easy option for them to know about this, and that stuff's not well publicized. Those are the kind of work I think we got to do to promote SPDK, right? So this is an older one too. I got to update because I saw it this morning. I'm always behind. I'm 1 year behind. I was here last year, and I got this. So yeah. So here's what I want to see next year, though, if I'm still alive and I'm here. The integration box, I want that to be the biggest part. That's what I care about. I mean, that's the part I care about because from a customer perspective, it's that. And then I want something like Rook on there. I want other integrations. And I want also what we can do is make SPDK, I guess we got to work on things to make it, it's good, it's easy to install. I don't know what the problems are, but I got to talk to my customers and figure out what the feedback is, and then promote it, and then have these guys more involved in the community, and have them fork the code, and have them integrated, and stop using iSCSI, because iSCSI is going away. You got to use NVMe, and then if they have bottlenecks in storage, SPDK. Very simple to me. All right, last slide. All right, what do I want to say? Oh, right, the other people that I'm going to pick on, or not pick on, but actually ask a kind request from. The 3 people who rule the world right now. No, it's not the president or anything like that. Or it's Andy Jassy, it's Dan Green, like whoever's running Google, whoever's running AWS, and whoever's running Azure. I thank them for contributing to the open source community, but they're making all their money off open source as well, so they could do more of it. So we need to be able to run something like, we need to be integrated with those stacks. Those stacks, I understand, are proprietary, but there could be versions of it that they could open source, and we got to integrate to that. Until then, we just got OpenStack, and that's the closest thing we got to integrate to. But I just hope those guys, offer like do something like Amazon did, which they do offer DPDK as a service on there, and they make it easy to do SPDK on there. But for example, Google Cloud hasn't figured that out yet. I can't do DPDK on Google Cloud. That's the problem. And then obviously I want to encourage you to keep coding, keep forking the. Try our code, see if you like it, give me feedback, whatever. But benchmark it, criticize it, hate it, love it. But also take SPDK, fork that, or contribute to it. Send pull requests. Listen, we live in exciting times. We're more connected than ever. I'm going to quote somebody, Steve Jurvetson. Anybody who know who that is? That's my favorite venture capitalist, and I usually don't like venture capitalists. He said, ideas are having sex, and new ideas are emerging because of this. So we have all this stuff. We just need to, I think, and that's why we're here. We did all this work, but I don't think we did a good job of promoting it. Have you guys ever heard of us before? Have you guys ever didn't know we have SPDK solutions for you? No. So a lot of things is internal. And by the way, at the corporations you work with, they're probably going to be against open source. But I encourage you to go there and fight that battle. I lobby for it internally myself. And also the future of all this is going to, obviously now the cloud's kind of, everyone's moving to the cloud. But after that, I told you about the 3 trends: hardware commoditization, open source, migration to the cloud. Seems like now there's a rival to the cloud. Now people are moving off the cloud and going onto Ethereum and Cardano. I didn't know you could run applications on a cryptocurrency blockchain. I thought it was for dumb money. But no, it's actually, you can run your apps there. You guys do DApps and decentralized apps. So that's where things are going. And so we got to also keep track of what those people are doing and the issues they're having. And again, we can solve it, especially that those blockchains are getting bigger and bigger. Size of blockchain is a big problem, and we can apply this technology, I think, to help those guys. Let's see. That is all I had.
I'm afraid to understand correctly, but you said you intercept socket API, so we don't have to customize SPDK, so we can use SPDK as is and integrating with your hardware and driver simply?
No, I think basically you're asking about how is our stack integrated into the hooks from there into SPDK? This is the best of my knowledge, but my engineers, what they've told me is just they've taken SPDK, they haven't changed it, and they've just to whatever API that's available, then they hooked our APIs into that. Meaning because when I asked them once, they packaged it all in one nice package to make it easy to install. I'm like, well, I have SPDK installed. Do I need to deinstall that? And they go, no. Even if you have SPDK, then you just do this part of it. So you just install this, and you don't. We just did that to make it easier for the user. That's my understanding. But then the details of it, I got to get from our engineering. I don't know. Sorry. All right. Well, thank you so much. Thank you for contributing to SPDK.